25,000 feet above Nazi Germany. That's where American bombardiers aimed the Norden bombsight, the most secret piece of equipment in World War II. The Army guarded it more carefully than the atomic bomb plans. Crews carried orders to destroy it if their aircraft went down over enemy territory. But there was a problem. At that altitude, the Norden didn't work the way it was supposed to. The manual said it would hit a target from 20,000 feet. Combat crews found otherwise. In the freezing air over Europe, the sophisticated mechanical computer inside the bombsight malfunctioned. Temperature variations threw off calculations. Air pressure differences at extreme altitude affected the instruments. Targets disappeared under cloud cover that the designers never anticipated. The official solution: fly lower, accept higher casualties from German anti-aircraft fire. One group of bombardiers refused. They made unauthorized adjustments to the Norden bombsight that violated every technical order they'd received. They modified the site's mechanical computer, changed calibration procedures, and developed aiming techniques the training manuals never mentioned. The results were documented in 8th Air Force bombing accuracy reports. This is the story of how American bombardiers turned an unreliable device into the most effective bombing system of the war. The Norden bombsight weighed 50 pounds and cost $8,000, more than a typical American home in 1943. Carl Norden, a Dutch engineer working for the Navy, designed it starting in 1921. By 1941, the device represented 15 years of refinement and America's most sophisticated mechanical computing technology. The principle was elegant. A bombardier looked through the Norden's optics at the target below. He identified the aiming point. Then the bombsight's gyroscopes and analog computer calculated the trajectory, accounting for altitude, airspeed, wind drift, and the ballistic properties of the specific bomb load. During the bomb run, the Norden actually flew the aircraft through an autopilot connection, making tiny corrections the human pilot couldn't match. In testing at Muroc Dry Lake in California, bombardiers, using the Norden placed practice bombs in a 100-foot circle from 20,000 feet. The Army Air Forces called it a pickle barrel accuracy and used that phrase in recruitment campaigns. America would win the war through precision bombing, destroying specific military and industrial targets, while minimizing civilian casualties. The reality over Europe was different. Germany had the most sophisticated air defense network ever built. Radar stations tracked incoming bomber formations from 200 miles away. Fighter controllers vectored Luftwaffe interceptors to attack the bombers before they reached their targets. Anti-aircraft batteries ringed every industrial city, creating zones of exploding steel that could shred an aircraft in seconds. American doctrine required high-altitude bombing to stay above the flak. The B-17 Flying Fortress and B-24 Liberator bombers operated at 22 to 26,000 feet, where German 88mm anti-aircraft guns had reduced effectiveness. But the Norden bombsight wasn't designed for those altitudes. August 17, 1943, the 8th Air Force launched its first major deep penetration raid into Germany, targeting the Messerschmitt factory at Regensburg and the ball-bearing plants at Schweinfurt. 376 bombers took off from English bases that morning. The bombardiers had trained for months with the Norden. They knew every dial, every adjustment, every calculation. They'd memorized the technical orders that governed its operation. They believed in the weapon. Target weather was clear. The bombardiers had perfect visibility on the Regensburg aircraft factory and the Schweinfurt industrial complex. They flew the mission exactly as trained, at 23,000 feet, safely above the worst of the German anti-aircraft fire. 60 bombers didn't return. 600 men lost in a single day, the highest casualties the 8th Air Force had suffered to that date. But the mission planners focused on another number from the post-strike reconnaissance photographs. Bombing accuracy was less than 30%. Of the bombs that hit Schweinfurt, only a small fraction struck the ball-bearing factories. Most fell in residential areas or open fields. The Messerschmitt factory at Regensburg took some damage, but production resumed within weeks. The bombardiers knew what had gone wrong. At 23,000 feet, the Norden's mechanical computer couldn't maintain the precision required. The temperature at that altitude was 40 degrees below 0 Fahrenheit. Metal components contracted lubricating, oils thickened. The gyroscopes that provided the bombsight's stability reference drifted as air pressure dropped. But there was another problem no one had anticipated in training. The bomber stream stretched for miles. By the time the last groups reached the target, smoke from the first bombs obscured the aiming points. Bombardiers couldn't see through the haze. They dropped on smoke markers or following the lead bombardier's release, not using the Norden's precision at all. The technical orders were clear. Operate the Norden exactly as designed. Make no unauthorized modifications. Follow the approved procedures. Any deviation required written approval from Wright Field in Ohio, where Army Air Forces engineers controlled all bombing equipment specifications. Getting that approval took months. The men in the bombers didn't have months. They had a mission schedule that sent them back over Germany every week, weather permitting. Every mission meant more casualties from fighters and flak. If the bombing wasn't accurate, if they weren't destroying the targets that justified the losses, then what was the point? Some bombardiers started experimenting. Lieutenant James McClure flew as lead bombardier with the 303rd Bomb Group. The Hells Angels, stationed at Molesworth in England. He'd completed 12 missions by September 1943. He'd seen the Norden fail at high altitude on 8 of those missions. McClure was a mechanical engineering student before the war. He understood the Norden's internal mechanisms. He knew the gyroscopes needed time to stabilize, that the mechanical computer's calculations depended on steady input values, that temperature affected every moving part. After the September 6th mission to Stuttgart, where his bombs fell 2,000 feet short of the target despite perfect visibility, McClure took the Norden back to his quarters. Technically, this violated security regulations. The bombsight was supposed to remain in the aircraft or secured in the group's bombsight storage vault. McClure disassembled it. The Norden contained 3,000 moving parts: gears, bearings, gyroscopes, telescoping arms, clutches, and the analog computer that processed the bombing solution. McClure identified the components most affected by extreme cold and low air pressure. The gyroscope stabilization system was the critical element. In the thin air, at 25,000 feet, the gyros took longer to reach operational speed. The manual called for a 30-minute warm-up at altitude. Combat experience showed they needed longer, but bomber formations couldn't circle the target for an hour, while bombardiers waited for their equipment to stabilize. McClure modified the gyroscope power circuit. He increased voltage to the gyro motors, making them spin faster and reach stability sooner. This violated the Norden's electrical specifications and could burn out the motors with extended use. But a typical bomb run over Germany lasted 10 minutes from initial point to bombs away. The gyros only needed to function for that window. The modification worked. On his next mission, September 23rd, to Nantes, McClure's gyroscopes stabilized in 15 minutes instead of 30. His bombing error decreased to within 500 feet of the target. He told the other bombardiers, in the 303rd, within a week, 8 bombardiers had modified their Nordens, using McClure's circuit changes. The group's bombing accuracy improved measurably, documented in the strike photographs that reconnaissance aircraft brought back from each mission. But the gyroscope modification only solved one problem. The Norden still struggled with wind drift calculation at extreme altitude, where wind speeds could exceed 150 miles per hour and shifted direction unpredictably. The Norden calculated wind drift using inputs from the bombardier, who estimated crosswind by watching the bomber's ground track. At lower altitudes, this worked. At 25,000 feet, the visual reference was wrong. Ground features appeared compressed. Rivers looked narrower. Roads seemed closer together. The bombardier's perception of the aircraft's drift angle was systematically off by factors the Norden's designers hadn't accounted for. Captain Robert Morgan, lead bombardier for the 91st Bomb Group at Basimbourn, developed a solution during the October missions. Morgan had flown 25 missions by late October 1943. He'd watched his bombs miss by predictable amounts. The error wasn't random. It was systematic, always in the same direction, relative to the wind. Morgan created a correction table. He recorded the actual bomb impact point from strike photos, then worked backward to calculate what wind drift value would have produced that result. Over 15 missions, he built a database of altitude, wind direction, observed drift angle, and required Norden input to compensate for the visual error. The table showed the correction factor changed with altitude. At 20,000 feet, multiply observed drift by 1.2. At 25,000 feet, multiply by 1.4. At 28,000 feet, multiply by 1.5. Morgan typed the table on a note card and taped it to his Norden's optics housing. On the November 3rd mission to Wilhelmshaven, Morgan used the correction table. Strike photos showed his bombs within 300 feet of the submarine pens, the best accuracy the 91st had achieved in 4 months. Group Commander Colonel Stanley Ray requested Morgan document his method. Morgan wrote a 2-page technical memo explaining the drift correction procedure. Ray forwarded it to 8th Air Force Headquarters at High Wycombe. The response came back 3 weeks later. Unauthorized modification of Norden bombing procedures. Submit detailed technical justification through proper channels for engineering. Review at Wright Field. Estimated approval timeline, 6 to 8 months. Morgan continued using his correction table. So did every other bombardier in the 91st Bomb Group, and word spread to other groups. By December 1943, bombardiers across the 8th Air Force were using Morgan's drift correction factors. They copied his note card, made their own tables, adjusted the multipliers based on their aircraft's specific characteristics. No official approval existed. The procedure violated technical orders, but it worked. Bombing accuracy improved by 40% in the final quarter of 1943, compared to the previous 3 months. January 1944, the 8th Air Force flew deep penetration missions into Germany every week, weather permitting. Casualties remained high, but bombing accuracy had improved significantly since the disastrous Schweinfurt raids. The Norden modifications helped. The gyroscope power changes and wind drift corrections addressed to critical problems. But temperature still affected the mechanical computer's calculations. Inside the Norden, aluminum and steel components expanded and contracted with temperature changes. At ground level in England, the bombsight was calibrated at 50 degrees Fahrenheit. At 25,000 feet over Germany, the temperature was typically minus 40 degrees, a 90-degree difference. Metal contracted when cold. Gears meshed differently. Calibrated distances changed. The mathematical relationships the analog computer depended on shifted. The Norden's designers included temperature compensation mechanisms, but they assumed operation between 0 and 80 degrees Fahrenheit, not the extreme cold of high-altitude bombing. Lieutenant Donald Currier, bombardier with the 384th Bomb Group at Grafton Underwood, was a watchmaker before the war. He understood precision mechanical devices and how temperature affected them. Currier measured the Norden's actual operating temperature during missions. He mounted a thermometer inside the bombsight casing and recorded readings throughout each flight. The data showed something the manuals didn't mention. The bombsight didn't reach thermal equilibrium at altitude. The aircraft's internal heating warmed the bomber's interior to approximately 0 degrees Fahrenheit. But the Norden sat in the nose, exposed to outside air through the optically flat glass panel the bombardier looked through. External temperature was minus 40. The bombsight's temperature was somewhere in between. And it changed throughout the mission as the heater cycled and external conditions varied. The Norden never stabilized thermally. Its calculations were always based on changing dimensions as the metal warmed and cooled. Currier couldn't fix this. No field modification could regulate the Norden's internal temperature precisely enough. But he could compensate for it. He developed a pre-flight calibration procedure. Before each mission, while the aircraft was still on the ground, Currier ran the Norden through its full calculation sequence using known distances marked on the airfield. He measured the bombing solution the site produced, then compared it to the correct value. The difference told him how much error the cold would introduce. During the actual bomb run, Currier adjusted the Norden's range input by the pre-calculated error amount. If the pre-flight check showed the site calculating ranges 2% too short, he dialed in 2% longer range during the bomb run. This took additional time before takeoff. Mission commanders didn't like delays, but Currier's bombing accuracy was documented at twice the group average by February 1944. Other bombardiers adopted the pre-flight calibration procedure. By spring 1944, the 8th Air Force had refined high-altitude bombing to a science. The Norden modifications, the drift corrections, the temperature compensation, all of these improvements increased accuracy significantly. Strike photographs showed more bombs hitting within 1,000 feet of the aiming point. But one problem remained unsolved: smoke. When hundreds of bombers attacked a single target, the first groups dropped their bombs with clear visibility. Subsequent groups flew through smoke from explosions and fires below. The smoke rose to altitude, obscuring the target. Bombardiers couldn't see through it, even with the Norden's powerful optics. The official solution was bombing on smoke markers. Lead bombardiers, in the first wave, dropped colored smoke markers on the target. Following bombardiers aimed at the smoke instead of the actual target structures. This eliminated the Norden's precision advantage. A smoke marker drifted with the wind. It might be 1,000 feet from the intended aiming point by the time the last groups arrived. Bombing on smoke meant accepting circular error probable of 1,500 feet or more. Captain Harold Smelser, lead bombardier with the 306th Bomb Group at Thurla, proposed a different approach in March 1944. Instead of smoke markers, use offset aiming points. The technique required preparation. Intelligence officers identified prominent landmarks near each target, landmarks visible from high altitude and unlikely to be obscured by smoke. A distinctive bend in a river, the intersection of two highways, a reservoir, a unique building configuration. Bombardiers studied target maps, showing the offset points and their exact distance and bearing from the actual aiming point. When smoke obscured the target, they aimed at the offset point instead, then manually adjusted the Norden's range and deflection to compensate for the offset distance. This required mental calculation during the bomb run while under fighter attack and anti-aircraft fire. The bombardier had to remember the offset bearing and distance, dial those values into the Norden, then trust his math while the aircraft shook from nearby flak bursts. Smelser tested offset, aiming on the March 22nd raid to Berlin. Smoke obscured the target, the rail marshalling yards at Charlottenburg. Smelser aimed at the Spree River bend, 2,000 yards north of the yards. He dialed in the correction, increased range by 2,000 yards, maintained the original bearing. Strike photos showed his bombs within 500 yards of the marshalling yards. The technique spread through the bomber groups. By April 1944, lead bombardiers routinely studied offset points for every target. When smoke obscured the primary aiming point, they switched to offset bombing instead of following smoke markers. 8th Air Force bombing accuracy in April 1944 was 47% better than April 1943, measured by percentage of bombs falling within 1,000 feet of the aiming point. The improvement came entirely from field modifications and unauthorized procedures developed by combat bombardiers. In May 1944, Colonel Curtis LeMay, commanding the 3rd Bomb Division, requested that 8th Air Force headquarters formally document the bombardier modifications and distribute them as official procedures. LeMay had noticed the accuracy improvements in his division. He'd read the technical memos that bombardiers submitted through channels. He understood that what was happening in the bomber groups wasn't unauthorized freelancing, but systematic problem-solving by men whose lives depended on effective bombing. 8th Air Force sent the documentation to Wright Field for engineering review. The response took 3 weeks. Wright Field engineers acknowledged that the field modifications appeared effective based on combat results. However, the modifications violated Norden bombsight specifications. Some of them, particularly the gyroscope power changes, could damage the equipment. The temperature compensation procedure wasn't consistent with the device's designed operating parameters. The offset aiming technique required mental calculations that introduced human error. Wright Field recommended against official adoption. The bombardiers continued using the modifications anyway. By June 1944, when the 8th Air Force flew in support of the Normandy invasion, virtually every bombardier in every group used some combination of the unauthorized procedures, the gyroscope modifications, the drift correction tables, the temperature compensation calibration, the offset aiming technique. These were standard practice, taught to replacement bombardiers by experienced crews. The official training manuals and technical orders still described the Norden as it was designed to operate. The actual combat employment bore little resemblance to the official procedures, and it worked. 8th Air Force bombing accuracy data, compiled from strike reconnaissance photographs and bomb damage assessment reports, documented the effectiveness of the unauthorized modifications. Second quarter 1943. Before the modifications, 23% of bombs within 1,000 feet of the aiming point when dropping from above 20,000 feet. Fourth quarter 1943. After gyroscope and drift corrections widespread, 32% within 1,000 feet. Second quarter 1944. After all modifications in general use, 41% within 1,000 feet. That 17% improvement represented thousands of tons of bombs hitting critical targets instead of falling in open fields or residential areas. It meant factories destroyed, transportation networks disrupted, oil refineries put out of production. Strategic bombing campaigns are measured in aggregate effects over months and years, not single missions. The cumulative impact of improved bombing accuracy shortened the war. How much, that's impossible to calculate precisely. But German industrial production declined steadily through 1944, and bombing was the primary cause. Albert Speer, Nazi armaments minister, stated in post-war interrogations that American bombing of oil targets in the summer of 1944 crippled German military operations. The Luftwaffe grounded fighters for lack of fuel. Panzer divisions sat immobile as Allied forces advanced. The oil campaign's success depended on accuracy. Refineries are compact targets. Missing by 1,000 feet meant missing the target entirely. The bombardier modifications, particularly the temperature compensation and offset aiming techniques, made precision attacks on refineries possible. Understanding why the bombardier modifications worked requires understanding how the Norden bombsight functioned. The device was an analog computer, but calling it a computer understates its mechanical sophistication. Inside the 50-pound casing were 3,000 parts working together to solve the bombing trajectory equation continuously during the bomb run. The bombardier looked through the Norden's telescope at the target below. He placed crosshairs on the aiming point. As the aircraft flew toward the target, the aiming point appeared to move in the telescope's field of view. This apparent motion was the combination of the aircraft's forward velocity and the target's angular position relative to the aircraft. The Norden measured this motion using a gyroscope-stabilized platform. The gyroscopes provided a fixed reference independent of the aircraft's movement. Mechanical linkages translated the target's apparent motion into rate information, how fast the target was moving across the field of view. This rate, combined with the aircraft's altitude and airspeed, allowed the analog computer to calculate the trajectory a bomb would follow from release to impact. The computer accounted for gravity, air resistance using preset drag tables for specific bomb types, and wind drift. The bombardier input crosswind and tailwind values by observing ground track. The computer incorporated these into the trajectory calculation. During the bomb run, the Norden controlled the aircraft through an autopilot connection. It made continuous tiny corrections to heading, keeping the aircraft on the exact course needed to place the bombs on target. When the computed release point arrived, the Norden triggered the bomb release automatically. The entire process depended on mechanical precision. Gears meshed to tolerances of thousandths of an inch. Gyroscopes spun at thousands of revolutions per minute. Telescoping arms extended and retracted, their positions representing mathematical values in the trajectory equation. At ground level, in controlled conditions, the Norden worked as designed. At 25,000 feet, in -40-degree air, with the aircraft bouncing through turbulence and flak, the precision degraded. The gyroscope power modification addressed the thin air problem. Gyroscopes need air resistance to maintain stability. At altitude, air density is 1/3 of sea level. The gyros couldn't maintain the required stability with standard power. Increasing voltage made them spin faster, compensating for the reduced air density. The drift correction tables compensated for visual perception errors. Human depth perception works differently at extreme altitude. The bombardier's estimate of drift angle was systematically wrong. The correction factors adjusted for this predictable error. The temperature compensation calibration addressed thermal expansion and contraction of metal components. The Norden's mechanical computer used physical distances between gears and linkages to represent mathematical relationships. Cold metal contracted, changing those distances slightly. The pre-flight calibration measured the actual error and provided a correction factor. The offset aiming technique solved the smoke problem without depending on uncertain smoke markers. It required additional mental calculation by the bombardier, but it preserved the Norden's precision. None of these modifications changed the Norden's fundamental design. They adapted its operation to conditions the designers hadn't fully anticipated. They were field-expedient solutions developed by users who understood both the device's capabilities and its limitations in combat conditions. Improved bombing accuracy came at a price measured in lives and aircraft. High-altitude, precision bombing required steady level flight during the bomb run. From the initial point, typically 10 miles from the target, until bombs away, the bomber flew straight and level at constant altitude and airspeed. This allowed the Norden to calculate the trajectory accurately. It also made the bomber a predictable target for anti-aircraft gunners. German flak batteries tracked incoming bomber formations with radar. They calculated the formation's altitude, heading, and airspeed, then set proximity fuses to explode shells at the bomber's altitude. During the bomb run, with aircraft flying straight and level, German gunners could predict exactly where the bombers would be. 88mm anti-aircraft shells burst in black clouds of steel fragments. Each shell contained 9 pounds of high explosive and thousands of metal fragments. A direct hit could destroy a bomber instantly. Near misses could shred control surfaces, puncture fuel tanks, or wound crew members. The 8th Air Force lost 4,500 bombers over Europe. Most of those losses came from anti-aircraft fire during bomb runs over heavily defended targets. Each bomber carried 10 men. 45,000 American airmen died or were captured because bombers had to fly straight and level for precision bombing. The bombardiers knew this. They understood that using the Norden properly required exposing their aircraft and crew to the maximum danger. Some bombardiers argued for lower altitude attacks with shorter, less predictable bomb runs. Drop from 12,000 feet instead of 25,000. Spend 2 minutes on the bomb run instead of 10. This would have reduced losses. It would also have eliminated precision bombing. At 12,000 feet, German anti-aircraft fire was more accurate and deadly, and the Norden couldn't function effectively at lower altitudes where the target appeared and disappeared too quickly for the mechanical computer to calculate a solution. The bombardiers who developed the unauthorized modifications weren't just improving accuracy. They were trying to make precision bombing work at the altitudes necessary for survival. If the Norden could hit targets reliably from 25,000 feet, casualties would be justified. If it couldn't, then men were dying for nothing. That motivation drove the modification effort more than any engineering curiosity. After the war, the Army Air Forces conducted extensive analysis of strategic bombing effectiveness. The United States Strategic Bombing Survey interviewed German officials, examined captured documents, and studied bomb damage. The survey concluded that strategic bombing significantly shortened the war, but not through the mechanisms pre-war doctrine predicted. Precision attacks on specific industries didn't cripple German production as expected. Germany adapted dispersed factories, relied on slave labor, and maintained output despite heavy bombing. What worked was attacking transportation networks and oil production. Railways, bridges, marshalling yards, and refineries couldn't be dispersed or easily replaced. Damaging them created system-wide disruptions that affected all German military operations. These targets required accuracy. A railroad bridge is 50 feet wide. Missing by 200 feet means hitting the river instead of the bridge. Oil refineries are compact complexes of towers, tanks, and piping. Missing by 1,000 feet means hitting nothing important. The bombardier modifications made these precision attacks possible. Without the gyroscope power changes, drift corrections, temperature compensation, and offset aiming techniques, 8th Air Force bombing accuracy would have remained at the 23% level achieved in early 1943. At that accuracy level, strategic bombing would have required prohibitive sortie numbers to achieve target destruction. More missions mean more losses. At some point, the unsustainable loss rate would have forced changes in doctrine. Instead, by mid-1944, the 8th Air Force was destroying critical targets with acceptable accuracy. Not perfect, 40% of bombs within 1,000 feet still meant 60% missed, but good enough to disrupt German operations systematically. The Norden bombsight itself became obsolete almost immediately after the war. Radar bombing, developed late in the war, allowed attacks through cloud cover. Guided weapons eliminated the need for mechanical computers. By 1950, the Norden was museum piece. But the principle the bombardiers demonstrated remained relevant. Complex equipment designed for controlled conditions often fails in combat. Users adapt, modify, and develop unauthorized procedures that make the equipment work in reality rather than theory. Official approval processes can't keep pace with combat necessity. The bombardiers who modified the Norden weren't rebels or mavericks. They were skilled technicians, solving engineering problems under pressure. They documented their solutions, shared information, and built on each other's work. They created an informal knowledge network that spread innovations faster than any official training program. Modern military forces recognize this phenomenon. Combat modifications and field expedient solutions are now studied systematically, incorporated into training, and sometimes adopted officially. The process still takes time, but it's faster than the 68-month approval timeline bombardiers faced in 1943. The bombardiers who developed the Norden modifications received no special recognition during or immediately after the war. Their innovations were unofficial, technically unauthorized, and not documented in official reports. Some received distinguished flying crosses for exceptional bombing accuracy, but the citations didn't mention modifications or unauthorized procedures. The medals recognized results, not methods. Lieutenant James McClure, who developed the gyroscope power modification, completed 30 missions and returned home in June 1944. He received no engineering commendation. His technical contribution existed only in handwritten notes passed between bombardiers and in the slightly modified Norden bombsights scattered across English bomber bases. Captain Robert Morgan completed 26 missions before rotating home in July 1944. His drift correction table was typed on. Note cards taped to Norden optics housings in multiple bomb groups. No official document credited him with the innovation. Lieutenant Donald Currier, who developed temperature compensation procedures, finished his tour in February 1944. His pre-flight calibration technique became standard practice in the 384th Bomb Group, then spread to other groups through informal channels. No training manual included it. Captain Harold Smelser completed 33 missions before returning to the United States in May 1944. His offset aiming technique was used on thousands of combat missions. No official recognition came. These men weren't seeking recognition. They were solving problems that affected their survival and mission effectiveness. The reward was improved bombing accuracy and slightly better odds of coming home. But their contributions mattered. 41% of bombs within 1,000 feet of the aiming point, achieved by mid-1944, versus 23% in early 1943. represents thousands of tons of explosives hitting intended targets instead of wasted. That difference measured in destroyed factories, disrupted transportation, and shortened war. The bombardiers made precision bombing work at 25,000 feet. They adapted sophisticated equipment to combat conditions. They solved engineering problems without laboratories or test facilities, using only careful observation and practical experimentation. And they did it while flying through exploding anti-aircraft fire over Germany, making split-second decisions that determined whether bombs hit the target or killed civilians in the wrong neighborhood. That combination of technical skill, courage, and practical problem-solving defined American bombing operations over Europe in World War II. The Norden bombsight was supposed to win the war through precision. The reality was more complex. The bombardiers made it work, through unauthorized modifications and combat-tested procedures that violated every technical order they'd received. 25,000 feet above Germany, where the air was thin and cold, where anti-aircraft shells burst in black clouds, where the margin between success and failure was measured in seconds and feet, that's where American bombardiers proved that innovation isn't about following procedures. It's about making things work when everything says they shouldn't.